So, welcome back. Now we'll be dealing with the next topic in your syllabus, that is Hagen-Poiseuille equation. Now, the next topic, probably the most important topic in this unit, is steady laminar flow in circular pipes. This is also called as Hagen-Poiseuille law. Now, what is Hagen-Poiseuille law or steady laminar flow in circular pipes? We deal with deriving the relations for velocity, pressure difference for flow. These both relations will be dealing here. Now let us consider a pipe of certain diameter d. In this pipe, let us consider 2 points. Point number 1, point number 2. These 2 points, they will be on the same horizontal line. There will be flow inside the pipe. The average velocity of the pipe will be taken as V. This is the average velocity of the pipe. Now, the next thing we'll do is apply Bernoulli's equation to this particular pipe flow. Considering 2 points, what will happen when we take Bernoulli's equation? It will become like P1 by rho g or P1 by W plus V1 square by 2g plus Z1 is equals to P2 by rho g plus V2 square by 2g plus Z2 plus HF. Why HF? Because there is losses inside the pipe. That is what this whole unit is about. We are considering losses, but there will be laminar losses, not higher losses like turbulent flow and everything. So here, since we know these points are on the same horizontal line, which means Z1, Z2 are same, they get cancelled. What is the thing that you can notice in this diagram is discharge through the pipe is constant because there is no change in area or everything. Whatever flow comes from here, that comes out here. So Q is constant. Q, that is discharge, is constant, which means Q discharge at 1.1 Q1 is equals to discharge at 0.2. What is Q1? A1 V1 is equals to A2 V2. There is no change in area between 0.1 and 0.2, which means A1 is equals to A2. So A1 A2 goes, V1 is equals to V2. That is, which means the velocity is same at both the points that we have considered. Now since it is same, we'll take V1 is equals to V2 is equals to V. Why are we taking V1 is equals to V2 is equals to V? To simplify the process of calculation. Because since we are considering 2 points here, if they both are constant, why not take a singular value, right? Now what will happen to this equation? V1 is equals to V2, so this gets cut off. From there, what will happen to Bernoulli's equation? P1 minus P2 by rho g is equals to HF. That is, the head loss is equals to change in pressure or decrease in pressure divided by the specific weight of the fluid. This is this equation we've already seen earlier also. We are just reiterating that this is how it is. This also means that pressure gradient, this is the pressure gradient, P1 minus P2 by rho g. Pressure gradient must decrease in the direction of the flow. Pressure gradient must decrease in the direction of flow in order to overcome the resistance of flow. Which offers the resistance? Shear stress. That is, resistance here means shear stress. Now, in deriving the equation, we'll move on to the next concept. While deriving, what we'll take is, we'll take a pipe. This is the pipe, and we'll take a cylindrical element, because a pipe in a 3D direction is a cylinder actually. If we consider pipe in a small element, this is a cylindrical element. This thing we'll consider this is the side view. I mean, this side view. When you view from this side, this is the view of the element that we are considering. The element, this is the element that we are considering with a radius small r. The total radius of this pipe is capital R. Small r is the distance of the element from the center, and capital R is the radius of the pipe. This dr is the thickness of the element that we are considering. Because if we consider an element, say this thickness here is similar to this thickness here. That is what here we are considering. Now, we've already seen how pressure and shear forces are related to each other. How shear stress shear stress in the vertical direction is equals to the pressure in the horizontal direction. Now, if we consider this particular element, what are all the forces acting on the element? One is pressure force from this side, that is this one. Second one is shear stress, that is this one. And another thing is another pressure force, that is this one. So, of this total, since there are these are the total forces acting on this particular element. What is this dx? Dx is the length of the element. Here dx is synonymous to length of the cylinder. If we take length of the cylinder as L, then length of this particular element is dx. Now let's go into the next one. We know here shear stress is the only resistance offered to the flow. There is no resistance from outside. Only shear stress is the resistance being offered. What overcomes this resistance? Pressure forces. Pressure force overcomes the resistance given by the shear stress. Now what happens? The summation of these forces in horizontal direction is 0. Why it is 0? Because there are no external forces acting. Only pressure and shear stress are acting. Pressure decrease is equals to shear stress increase, right? Since only pressure is used to overcome shear stress, it means how much ever decrease is there in pressure is equals to the increase in the shear stress. That is, let us take in the horizontal direction. In horizontal direction, what is this? This is right side, P into pi r square. Why pi r square? Pi r square is the area. We are dealing with forces here. P into pi r square minus, what is next here? P plus dou p by dou x into dx into again pi r square. Good. This is the pressure forces, and minus tau into 2 pi r dx. Why tau into 2 pi r dx? See, pressure force acts along the cross sectional area. See, this is a circle with radius r. Pressure acts like this, whereas shear stress acts in the tangential direction. Tangential means circumferential area. What is the circumference of the circle? 2 pi r. Since the circumference is 2 pi r, and since it is acting over length of dx, the total area will be 2 pi r into dx. That is the area over which a shear stress acts. Now we'll solve this. P into pi r square minus P into pi r square minus dou p by dou x to dx into pi r square minus tau into 2 pi r dx is equals to 0. So this one goes. Now dou p minus dou p by dou x into dx into pi r square is equals to tau into 2 pi r into dx. R pi dx. From this what we get? minus dou p by dou x into r is equals to 2 tau, which means tau is equals to minus dou p by dou x into small r by 2. This equation is shear stress over the fluid element at a radius small r. That is, if we take an element which is at a radius of say r, some value, it can be 1 meter, 2 meter, 3 meter, whatever is inside the pipe, then the shear stress will be given by this expression, which means tau here is directly proportional to small r, which means the more the distance of the particular point from center is, the more the shear stress will be at that particular point. Now, if say we are considering a fluid element at the pipe wall, that is where small r is equals to Kepler. Kepler is what? The radius of the pipe. That is, at the wall, radius will be Kepler. So what will happen? Tau is equals to minus dou p by dou x into capital R by 2. This is tau naught, that is shear stress at wall. Now, what will happen if we consider at the center of the pipe? What is the radius at the center of pipe? Radius means if we consider an element at the center of pipe, the distance from the center is 0. That is small r is equals to 0 at center. So tau at center is equals to minus dou p by dou x into 0. That is what we got. Tau at center is equals to 0. We already discussed this, but now this expression proves that what we discussed and what we derived is correct. In this expression we see tau is directly proportional to r. Say if change of pressure with respect to length is constant, then tau is proportional to r, which means the relationship of shear stress is linear, which means as r increases, tau increases. Since we've discussed or we've proved that shear stress is linear with respect to the radius, we'll see why there is minus here. Why minus? See, we know shear stress is positive because shear stress increases. If shear stress increases, which means it is in the positive direction, then whatever value we should get here should also be positive. But what we know is as we go throughout the length of the pipe, pressure decreases because that is the only thing that compensates for shear stress increase. Pressure decreases means dou p is negative. Change in pressure is negative. Change in pressure is negative, and which means minus dou p by dou x is positive. Why is it positive? See, dou p is already, that is pressure is negative only. Pressure decreases, that is minus. Pressure decreases along the length of the pipe. This is already negative. So now minus into minus is plus, which means tau is positive, shear stress is positive, and change in pressure is negative. Now let's see another equation form that we can derive from this particular relation. What is the expression for tau that we already know? Tau is equals to mu du by dy, or tau is equals to mu dou u by dou y. Dou here, why? Because since dou is partial differentiation, d is absolute differentiation. D is absolute differentiation. Dou u by dou y here means partial differentiation with respect to y direction. Since here our velocity varies only with this length, that is what we are considering. Shear stress varies with only, not velocity, shear stress varies with only y direction. We'll be considering only differentiation with respect to y. Same follows for pressure also. Since the pressure is only changing in x direction, our pressure will be dou p by dou x only. There won't be dp by dx or dp by dy or dou p by dou. So now from this, what we have, we'll know dou u. Dou u remains as the same. Y is distance from wall. Say if you take a plate like this, and if there is flow happening over this like this, then to calculate shear stress at a particular point, we take y is distance from the plate. In this case, in our pipe flow, walls are at both directions. Both are walls, which means here y can be written as capital R minus small r. This is capital R, sorry, D. That is from center, this is small r. And if we take an element like this, this is small r. See, this is capital R, this is small r. From wall, this is the distance y. I'll write another color. The distance is y. What can be seen from here? Y is capital R. Y is capital R minus small r. Now, from here we know what y is. What will be dy? Dy is d of r minus r. That is dy is minus dr. Why? R is constant value. R is a fixed value. The radius of the pipe is fixed. Derivative of a constant is 0. Whereas this small r, this is a variable value. If we take, say here I've taken this small element. If say I take another element here, okay, like this, then that radius will be say r2 something. But no matter what, this r value, capital R value, it won't change. This value, it will keep on changing. That is the way we assume it. Wherever we are assuming it, it changes. So now dy is equals to minus dr. We'll use this in this equation, that is in the tau equation. Tau is equals to minus mu dou u by dou r. Minus I'm already taking. What did we get the expression for tau as here? Tau is equals to minus dou p by dou x into small r by 2. We'll use that here. Is equals to minus dou p by dou x into small r by 2. See, minus minus goes. We'll rearrange the terms. Dou p by dou x is equals to 2 mu by r into dou u by dou r. See, we are rearranging the terms now. From here again, dou u by dou r is equals to 1 by 2 dou p by dou x into 1 by mu, r by mu, sorry, which means dou u by dou r is equals to 1 by 2 mu into dou p by dou x into small r. The next step to find out u, here we have dou u by dou r. This change in velocity with respect to radius. That is what this expression means. Now in order to get u, we have to integrate. Okay. We integrate. While integrating, we see here dou u can be written as 1 by 2 mu into dou p by dou x into r dou r. See, r dou r is there. We can easily integrate it, but dou p by dou x is also there. We don't know if it is a constant value or a value that depends on r. If it depends on r, then the formula will change. We have u v, derivative of u into v, that is u dv plus v du kind of. But See, in earlier equations and all, what we derived is pressure changes only with respect to length, that is in the horizontal direction. In vertical direction, pressure is constant, which means vertical direction is here radial. Radial is also vertical direction only. Like this is the pipe. Then this, if we take this radius is also vertical direction. So dou p by dou x is constant with respect to r. This value can be termed as a constant value. That is, this is a constant. Why it will be useful in deriving all this? So we integrate u, the integration of dou u is u 1 by 2 mu into dou p by dou x. Now r dr or dou r, what will happen to it? R square by 2 plus c. What is c? Integration constant. We don't know what it is, but it is a constant. In order to find c, we'll apply the boundary conditions. What are the boundary conditions at wall? That is at small r is equals to capital R. What is the velocity? Velocity is 0. Because why? See, here there is the pipe, flow is happening. Okay. Here one fluid layer will exert some pressure or resistance over another fluid. What happens at this point, that is at the boundary point? Here flow, see, velocity of this flow is some, velocity of this layer is some, velocity of this layer is some, velocity of this layer is some. What happens at this point, since velocity of the wall itself is 0, wall is not moving anywhere, which means the velocity of wall is 0. What happens? Any fluid layer that is closely attaching, like see, we are zooming in so much that we are considering that minute layer which is in contact with the wall. What happens to that layer? It will almost remain in rest because this has higher resistance, the wall has higher resistance, and the next layer that is attaching to the wall will also be 0, whereas that next layer which comes after this, that will have a little bit more velocity. It will have a little bit more velocity, then there will be another layer which has a little bit more velocity. That way velocity increases. That is what profile of velocity means here. Now, so at r is equals to r, velocity is 0. We'll apply this over here. What will happen? U is equals to 0 is equals to 1 by 4 mu into dou p by dou x into r square plus c. Since this is 0, what is c? Minus 1 by 4 mu to dou p by dou x into capital R square. This will apply in that equation, which means u is equals to 1 by 4 mu into dou p by dou x into small r square minus 1 by 4 mu into dou p by dou x into capital R square. This is c. This expression is the integration constant that we are getting. Now we'll take out the common terms, and 1 by 4 mu into dou p by dou x into small r square minus capital R square. We can write this as u is equals to minus 1 by 4 mu into dou p by dou x into capital R square minus small r square. This is the expression for velocity in a steady laminar flow through a circular pipe. This expression is quite an important one. This shows how velocity varies with respect to the pressure gradient and radius inside the pipe. Now this is just the first part. We thought about deriving the equations for velocity and pressure. This is just the equation for velocity. The equation for pressure, the equation for discharge we'll be seeing in the next part. So we'll see how they are derived and what are their significance in the next part. Thank you.